In computational drug design, the ultimate objective is predicting the precise binding affinity between a target protein and a potential ligand. We define this affinity quantitatively as the Gibbs free energy of binding, or delta G bind. This is the free energy difference between the bound complex and the completely separated unbound states. That delta G value is directly related to the equilibrium dissociation constant, Kd. It depends on the average probability of finding the molecules in the bound versus unbound states within an aqueous solution. To calculate that probability from physical simulation requires observing multiple binding and unbinding events. But tightly bound complexes only dissociate on microsecond to millisecond timescales. Standard molecular dynamic simulations typically run on the scale of nanoseconds. To capture a single physical dissociation event would require running these atomic-level calculations thousands to millions of times longer than current hardware allows. Because the system gets trapped in local energy states, a multiple minimum problem, the simulation will stall out in the bound conformation long before a dissociation event ever occurs. Direct physical simulation of drug unbinding is computationally intractable. To solve the equation, we have to bypass physical reality entirely. The mathematical loophole that makes this bypass possible is that Gibbs free energy is a state function. In thermodynamics, the total change in energy for a state function depends only on the starting and ending states. It is completely independent of the path taken to get between them. Computational chemistry exploits this property by abandoning the physical pathway of the ligand entering or leaving the protein pocket. Instead, researchers construct non-physical, mathematically convenient pathways in silico. These are known as alchemical thermodynamic cycles, and because of the state function rule, they compute the exact same delta G bind. We do not need to simulate reality to get real thermodynamic numbers. We only need a closed mathematical loop that mutates or deletes the molecule in place. The computational engines driving these non-physical pathways are free energy perturbation and thermodynamic integration. Both methods operate on a single control variable, the coupling parameter, lambda. By scaling lambda from 0 to 1, the algorithm smoothly transitions the interaction potential between two chemical states, effectively turning atomic interactions on or off without breaking the underlying simulation. While faster, less rigorous endpoint methods like MMPBSA exist to estimate energies, only lambda-dependent alchemical methods provide true thermodynamic integration. Lambda is the mathematical dial that allows us to slowly morph or annihilate atoms in a controlled, calculable sequence. When comparing two highly similar molecular structures, researchers use relative binding free energy, or RBFE, to calculate the difference in affinity, termed delta G. This diagram shows the thermodynamic cycle computing relative binding free energies. The horizontal arrows represent the physical binding process, which is mathematically prohibitive. The vertical green arrows show alchemical mutations. Ligand A mutates into ligand B first in the solvent, then inside the protein complex. By taking the free energy required for the mutation inside the complex and subtracting the free energy of the mutation in the solvent, the equation yields the exact relative binding affinity between the two ligands. Operationally, RBFE ranks a congeneric series of ligands, compounds sharing a common molecular scaffold. Because the atomic framework mostly remains identical during the simulation, RBFE avoids massive atomic disruptions. This efficiency makes it the pharmaceutical industry's primary workhorse for lead optimization. If we need to calculate a ligand's true independent binding energy, its absolute delta G bind, we use absolute binding free energy. This diagram illustrates the double annihilation thermodynamic cycle. On the left vertical leg, the ligand is annihilated in the free solvent, turning off its interactions until it becomes a ghost molecule. On the right, that exact same annihilation occurs while bound inside the protein complex. A strict requirement for absolute binding free energy is the use of positional restraints. Without physical restraints anchoring its center of mass, the decoupled ghost ligand would drift infinitely through the simulation box as its interactions vanished. Applying these restraints introduces an artificial loss of translational and rotational entropy. To correct this, complex analytical calculations are required to map the result back to a standard state volume of 1 molar. The absolute method is computationally expensive and mathematically tedious, but it is mandatory for scaffold hopping, comparing entirely different molecular structures to discover new classes of drugs. The benchmark for these calculations in drug discovery is predicting binding affinity with a margin of error of less than 1 kilocalorie per mole. Perfect alchemical math will still produce incorrect results if the simulation fails to accurately sample the target's highly rugged free energy surface. Standard molecular dynamics often lack the kinetic energy to overcome high-energy activation barriers, leaving crucial conformational states completely unvisited during the simulation run. In biological systems, proteins are highly flexible. The act of binding frequently requires massive structural rearrangements in the binding pocket. The simulation must sample two competing realities of binding: conformational selection, where the protein shifts into the bound shape before the ligand arrives, and induced fit, where the ligand's presence forces the protein to change. If an alchemical simulation morphs a ligand inside a protein that is trapped in the wrong biological conformation, the resulting thermodynamic data is compromised. To counter rugged energy landscapes, computational chemists apply enhanced sampling techniques. Methods like umbrella sampling and metadynamics apply artificial biasing potentials. This injects energy into the system, systematically forcing the simulation out of local minima. Overcoming sampling barriers is only one part of the solution. The physical parameters governing the atoms must also be precisely calibrated. This requires transitioning from computationally cheap implicit solvent models to expensive explicit solvent models, which accurately capture the structural and energetic effects of individual water molecules. The highest tier of accuracy integrates quantum mechanics with molecular mechanics, or QM/MM. This hybrid approach calculates exact electron polarization effects that standard classical force fields omit entirely. Reaching the 1 kilocalorie per mole threshold requires combining non-physical alchemical pathways with hyper-accurate, artificially enhanced physical sampling methods.